In just a few minutes, we'll start with the pitch session, and you'll see some four exciting brand new companies that most of you have never heard of. Thanks. Good afternoon, everyone. Welcome to another presentation here on the main stage. We're now going to have 5 of the cohort companies from the robotics factory give a pitch. A pitch, for those who don't know, is a short presentation, typically to an investor, in the hopes that they'll provide a check to help that company along. And we have 5 presentations from today from the latest robotics cohort of companies in the robotics accelerator at the robotics factory. So we'll start first with Mitch Fogelson, who is doing Beyond Reach Labs. All of these companies have interesting technology, and they're all different, by the way. They're not doing the same thing. So Mitch, can you come on up?
Thank you so much. How is everyone doing today? Robotics Discovery Day 2025. I'm going to take your robots into outer space. My name is Mitchell Fogelson. I am the founder and CEO of Beyond Reach Labs, where we are accelerating deployable space structure design with fast and accurate simulation tools. Today, there are 12,000 satellites in orbit around space, or as I like to say, 12,000 robots. And there's expected to be 100,000 over the next 5 years. While launch costs and hardware costs have continued to come down, the amount of design and prototyping exceeds $100 billion for these next 5 years to develop these new satellite systems. One of my favorite satellites is NASA's James Webb Telescope, which shows that in space, bigger is better. Larger solar arrays, space deployables allow for better communication, better power, better reflectors, but it comes with a risk. The James Webb Telescope experienced about $1 billion in unexpected late testing costs because designing systems here on Earth for space is very challenging, especially when they deployed the size of a tennis court. This accounted for around 10% of the overall cost of the James Webb mission. So that's why Beyond Reach Labs is building our virtual space studio for deployable systems. We accelerate design through generative design algorithms, simulation, and optimization, enabling engineering teams to accelerate their space system without the unexpected testing changes and design changes later stage. We save aerospace companies $1 million per design on average on unexpected prototyping costs. By our accelerated dynamic simulation, we're able to enable engineers to evaluate thousands of different satellite configurations, reducing rework by 50% and integrating into their existing CAD and simulation workflows. To date, we've primarily been funded through research grants by NASA, where we validated our simulation tool with a zero-G flight earlier this year. With the help of the Robotics Factory Accelerator Program and several other competitions, we've been able to secure our first pilot study with a leading space deployable company who's launching their deployables in 2026. And next year, we hope to extend our tooling to over 100 users, and by 28, 1,000 users to reach the growing satellite demands. This company was kind of founded through my research over my PhD at Carnegie Mellon, where I worked with NASA on kilometer-scale space structures for next-generation space stations. And my co-founder, Pele Collins, led SpaceX's parachute team for 38 successful missions across Dragon 1 and 2. So join us in expanding our innovation to space, and please reach out to me or come to our booth and try out our demo. Thank you so much.
Hello, from space now to the ocean. Hi, my name is Paul Grech, co-founder and CEO of Octopulse. We are building the future of autonomous aquafarming. Aquaculture is a $310 billion global market. It is the fastest growing food sector and projected to reach over $500 billion by 2050. However, operations in aquaculture are widely still very manual, resulting in high labor costs and reduced margins. Farm leaders know that in order for them to sustainably meet the growing demand for seafood and mitigate the harmful effects of overfishing, improvements in technology are required. There are many opportunities for improvement along the production process, but we are starting with two of the most labor-intensive bottlenecks in the on-land early stage part of production: phenotyping and deformity inspection. These are essentially the quality assurance, quality control steps in the production process. And for those that are not familiar with phenotyping, it is the measure of observable or physical traits on the fish to provide insights for selective breeding efforts. These processes are slow error-prone, and despised by technicians, but they are critical for the overall success of the farm, as they determine which fish make it out of the hatchery and into the main feeding stage, where farms are spending millions of dollars feeding fish until harvest. If deformed or weak fish make it through, they do not survive, and the risk of disease spreading and impacting healthy fish further cuts into overall efficiency and farm yield. We are solving this with a unified platform for phenotyping and deformity inspection. We start with phenotyping because it is a software-forward approach. It is the first step in the production process. It results in the eggs, and it is easily scalable across species and across the entire fish life cycle. Our platform combines computer vision and off-the-shelf hardware to cut inspection time from the 5 minutes that technicians are able to achieve manually per fish to under 30 seconds, and with over 90% accuracy, providing farms with unbiased, actionable insights that they can use to make corrective decisions in their selective breeding efforts to produce the next generation of fish to grow faster, be more disease resistant, and boost overall farm yield. We have completed 5 pilots to date, collected and labeled over 5,000 images, and with each deployment, we are further building on a robust multi-species data moat. We are finalizing a funded design partnership with the largest trout producer in the US, which at the end of 10 months will result in a production-ready phenotyping model validated for commercialization. Through transfer learning, we will quickly apply breakthroughs across species, deploying further through our beachhead of North America, where our target revenue per farm is around $150K. We will quickly begin global expansion to the more mature markets, salmon in Chile, salmon and trout in Northern Europe, bass and bream in the Mediterranean, and shrimp in Ecuador and Southeast Asia, where our target annual revenue per farm is over $500,000 across multiple model offerings. My co-founder Rohan and I met at Carnegie Mellon University. We are both from coastal backgrounds, and seafood is an integral part of both of our cultures. Our expertise in AI and aquaculture allows us to build scalable solutions to advance aquaculture while protecting the ocean. And we are supported by 3 advisors with deep seafood industry and technology experience, guiding us as we move from pilots to commercial launch and to our global expansion plans. We are targeting an $800K pre-seed over the next 6 months. Funds will be used to deploy further through our beachhead of North America, begin global expansion, starting with salmon in Chile and bass and bream in the Mediterranean. And lastly, for advanced R&D for the next phase of automation, which will bring in gantry and soft robotics to build towards true precision aquaculture. Starting with computer vision for phenotyping and deformity inspection to automation across the entire fish life cycle. We are building the autonomous aqua farm of the future. And if you'd like to learn more, let's connect. Thank you. Here we go.
Nice space. Oh, yes.
Thank you so much.
Thank you so much. All right, cool. So, all right, I'm Matt Travers. I'll be speaking on behalf of RoboLoop today, and we are delivering automation to e-waste processing. All right, so RoboLoop is a pre-existing e-waste processor with a facility in State College, PA. So our objectives are, number 1, to be able to increase the efficiency of our current manual workflows using custom robotic disassembly automation. And number 2, we ultimately want to scale our solution to other geographic regions. So why e-waste? So if we look at e-waste management globally, it actually costs the global economy around $37 billion a year today. And furthermore, if we look at the data of the rate that waste is actually growing relative to the rate that we are actually recycling that waste, we can see that this number is going to go up in a bad way in the coming years. So, however, if we look at this same report, what we ultimately find is that this is an industry that is ready for disruption. For example, at current recycling rates of 22%, again, we're losing billions of dollars a year. However, if we could reach this aspirational rate of 60% recycling, we could actually turn that into a profit of approximately $40 billion a year. And ultimately, this is where we see RoboLoop's greatest potential for impact is moving this number up and to the right. And we could potentially have an impact of approximately $75 billion a year. So why us? So I mentioned that RoboLoop is a pre-existing processor of e-waste. And what ultimately ended up happening is we took over the disassembly operations for a pre-existing business called eLoop that was started by my co-founder and current CEO, Ned Eldridge. So in taking over this operation, we actually started with some initial market traction. For example, we have existing upstream customers. We're currently providing disassembly services to 5 upstream recyclers today. We have access to downstream markets. Ned has over 17 plus years of navigating the ins and outs of ultimately where you sell material once you disassemble it. And finally, I'm currently a systems track faculty in the Robotics Institute at Carnegie Mellon, where I've spent the last 6+ years of my career working directly with a large OEM, focusing on developing AI and custom robotic solutions for the e-waste space. So some of the problems that are currently actually facing disassembly in the e-waste industry are that the existing solutions really fall onto one of 2 ends of a spectrum. On the one end of the spectrum, you have manual processing, which is very effective, but as you imagine, has very low throughput. On the other end of the spectrum, you have conventional automation, which has very high throughput, but unfortunately is very ineffective in the sense that it creates a lot of contamination and ultimately reduces the value of the materials that you actually go and disassemble. So RoboLoop's solution is basically a happy medium between these 2 extremes. So we're combining custom robotic automation that works safely alongside human workers to maintain the high throughput that we see from conventional automation while preserving the low contamination that we see from manual workflows. So in terms of productivity improvements, what we're seeing, so in State College today, we have 5 workers on a line who are focusing on disassembling flat panel displays. Those 5 workers are able to produce, on average, about 25, or able to process around 25 units per hour. So with the semi-automated workflow, like you see here pictured on the slide, we're projecting that that same number of workers could quadruple the output to 100 units processed per hour, which for us would represent an increase of 300% in revenue while keeping our labor costs fixed. Thank you very much. Please check us out at our booth. I'd be happy to share more.
Good afternoon, everyone. My name is David Dietrich, and I'm here to talk to you about silly surfacing. We're out to solve the pothole problems in roadways, parking lots, sidewalks, bike lanes, anywhere there's asphalt. Potholes, right? Not a sexy business, but it's a big problem. It's all over. And we in Pittsburgh understand potholes, don't we? Yes. Potholes account for 44 million accidents, 26 billion in damages, and unfortunately a third of those car accidents are fatalities. So what do we see out there today? 6 or 7 orange hats jump out of the vehicle. What do? Well, they throw some hot patch or cold patch in the hole. They don't even clean it out. There might be a tamper right behind it. They block traffic. It's a big disruption, right? Pisses everybody off. Well, we have the solution. We have a plan, a 4-step process. The 4-step process is we first come in and work with the client. And we sit down, we do some planning, we use Google Earth, the latest technologies that are available to us. Then we have a drone division. We send our drones out, and they actually scan the property to get accurate calculations of what the damage is, what areas are prioritized, what we need to do, and more importantly, so material calculations so that we know what we need as far as fixing the holes. This all is uploaded into the cloud, and so we're using AI and the latest technologies to help keep our robot fed with information. And so then we have our secret sauce, and that's our patent pending, silly surfacing, robotic robot pothole patcher. How about that? Yes, we are working on this, so it is going to be a reality, and it is going to see it here in Pittsburgh first. So we roll up onto the site. Guess what? 1 driver, not a team of 6 or 7 people. Eventually it'll be autonomous. Eventually it'll be battery operated, so we'll be green. But right now, we're rolling up exactly where we know we're going to fix the pothole. So we're doing LiDAR scanning in the front of the machine. And by the way, if you want to stop over at our booth, Dan set up a nice simulated pothole for you, and you can actually see LiDAR in action. We're then going to be cleaning out the hole, filling it with tack, then putting a hot or cold patch depending on the time of year. And then we're going to tamp it down. All this is going to be accurately measured by computer vision. So isn't that cool? Guess what? One more thing. All within a walking pace. So this thing is not going to stop. It's going to move in traffic. Very cool. So pothole repair costs out there today, they're in excess of $50 per hole. That adds up when there's a parking lot full of 20 or 30 holes. Also, to deploy a crew, it could be $100 to $250. There's asphalt literally everywhere that we turn. Our ultimate goal for the client is do it in half the time and half the budget. We have a stellar leadership team. And I can tell you this, we have over 75 years of entrepreneurial business experience and startup experience. So the acronym in our group is tremendous. We have Keith Giuliani, who is our founder, and his lovely wife back there. They are the innovators of this robotic pothole patcher. He's commissioned with Dr. William Clark, who is the scientific lead and also head of the Swanson School of Engineering, where we have these wonderful students and their mentors. They're helping us build this as we speak. So stop by the booth and you'll be able to see them. And then I also want to big a shout out to Dr. Dowling, then the wonderful mentors at the Robotics Factory. Thank you very much for all that you're doing for us. All this team effort is so we can get something out the door and in production here in Pittsburgh. My name is David Dietrich. I'm a board member, and I appreciate you listening to my spiel. So please come over and have a chat with us. We have a lot of neat stuff, and we'll see you on smoother roads ahead.
Hi, can you guys hear me? Hi, my name's Hannah. I'm the CEO and co-founder at Space Precision Systems. At SPS, we are solving one of the oldest, most persistent, most expensive problems within the space industry, which are leaking valves. Valves are a common component within different types of propulsive spacecraft, ranging from satellites to rockets. There's a lot of different types that have different functions, but the thing that they have in common is that they all leak. Valves are responsible for billions of dollars in costs related to unplanned labor and launch delays. If you hear about a major space failure in the news, it's probably because a valve has leaked and something needs to be fixed or replaced before the vehicle can fly. There's just a couple of examples on the slide here. In the best case scenario, it might be a couple $100,000 in lost test campaigns. In the worst case, it's literally loss of life. So this is a huge problem and one that NASA has consistently listed as a major technology gap. And the reason this is such a large problem is because the technology hasn't changed very much since the 60s. The core part of the valve that commonly breaks is the seal. They're typically made out of elastomer or polymer materials, which don't do well under heavy launch loads and wide temperature swings, both of which environments are common during launch, transit, and orbit. So at SPS, we found a way to make the seal out of metal. Notably, this is not just a materials change, it's also a geometry change, and we've designed the valve around that new geometry. Our preliminary seal test held water at 6,000 bar, which is 87,000 PSI. That's over 8 times the industry standard. And we're about to run a helium leak test, which is sort of the gold standard for checking valves within the space industry. Our valve has the potential to unlock a number of system-level efficiencies. There's massive opportunities, so obviously our patent is very important. We submitted a provisional patent this August, and we plan to keep some of the tech stack as a trade secret, in particular how to manufacture the seal. Unlike terrestrial concepts, space is a high-value industry, not a high-volume industry. To put this in perspective, a simple valve can cost $10,000 to $25,000, with more complex valves or regulators costing over $250 million. The valve supplier that supplies the rocket shown on this slide likely makes around $3 million per rocket in reoccurring revenue. One of their major competitors launched thousands of rockets last year. So you can see that in addition to this being a billion-dollar problem, there's also a billion-dollar opportunity. Biggest barrier to entry is the general risk aversion in the space industry. So it's essential that we heavily, particularly test with lots of oversight. We've proposed a couple million to NASA and the Space Force to do just that, and we'll take our testing results to leverage contracts with government and commercial entities. We also have a couple higher TRL level technologies, including gimbals and mechanisms, which might be more suitable to this audience today. So if you need a gimbal or a very precise mechanism, please come talk to us. And last but not least, we have the perfect team to execute on this plan. I have prior experience running a $320 million mission to the moon, so I understand this problem very deeply from the customer perspective. Also have prior experience in startups, IoT, and robotics. Daniel Sherwin is my co-founder. He invented the valve and is one of the best electromechanical engineers in the world. He has 4 decades of experience developing these types of systems and holds over 30 patents. And Gal Inbar has significant expertise on the operational and financial side, including robotics companies. So thank you for your time. If you want to learn more about our company or just chat about space in general, please stop by our booth.
Thanks everyone for attending the pitches. 5 companies with very unique applications and problems that they're solving. In just a couple of minutes here, we will be having a panel discussion with a couple of companies different than you just saw here on stage. But we'll be right back shortly. Thanks.